Hello, everyone. Thank you for joining us today on this webinar brought to you by the National Electrical Manufacturers Association. My name is Jonathan Stewart, and I'll be your host for the next 90 minutes or so. I'm the Senior Industry Director for Utility Products and Systems at NEMA. By way of background, NEMA's SF6 and Alternatives Coalition is an industry forum for discussion of SF6 and alternative insulation technologies as used in electric transmission and distribution equipment, as well as interaction with public officials surrounding emissions reporting and reductions regulations. As a group, so that everybody's aware, the coalition does not favor one approach to insulating medium and high voltage equipment over any other. Rather, we collaborate to provide education to public and private decision makers to fully inform their process. And that's exactly why we're here today, to help inform interested stakeholders surrounding some federally funded projects to develop non-SF6 technologies. We have three presenters with us today, each of whom will present on the early stages of an ongoing research design and/or development project, as well as the desired outcomes. Each presenter will have approximately 15 to 20 minutes to present, and then we'll have 5 to 10 minutes for Q&A before we move on. Please put any questions you have in the chat. At the end of each presentation, I will read and the presenter will answer as many questions as we have time for. While we do hope there will be several questions for each presenter in the chat, there will be no verbal audience participation today, so I've put everyone on mute. I'll also let everyone know that this webinar is being recorded and will be posted online at the Coalition website and LinkedIn page. I will put both URLs in the chat in a few minutes for your future reference. Our first presenter today is Dr. Lucas Graber. Dr. Graber is an associate professor at the Georgia Tech School of Electrical and Computer Engineering. He received his PhD in electrical engineering from Zurich in 2010. Before he joined Georgia Tech in 2015, he worked at the Center for Advanced Power Systems at Florida State University, initially as a postdoctoral research associate and later as a research faculty member. His research focus currently is on superconducting power cables and fault current limiters, cryogenic power electronics, mechanical and hybrid switchgear, and grounding of power distribution systems. With that introduction, I'll turn it over to Dr. Graber to talk about his project.
Thank you for the nice introduction, Jonathan. Can you hear me?
We can hear you great. Thank you.
Then let me share my screen. Can you see my screen?
Yes, we can.
All right, so hello everyone. Thank you for letting me present here. So what I'm presenting here is our work that we call Tesla, the tough and ecological supercritical line breaker for AC, or in other words, how we avoid using SF6 in our circuit breaker. Now, I would like to emphasize that this work is actually a large collaboration. There are several collaborators at Georgia Tech, including Jürgen Rauleder from aerospace, Santiago Grijalva, colleague from mine in electrical engineering, Jonathan, who helps us with tech to market needs, but then also Mississippi State University, where we have Chanyo Park contributing to the project, and my own research engineer, Jiang Jin, who has the project management function. Now, the first thing I would like to do is briefly look at the history of circuit breakers over the past, now about 100 years. The reason why I'm doing this, I may have an other look at this than others have in the past. What I see here is we initially started using a non-compressible liquid as an arc quenching medium. So initially water and then later bulk oil. Now they each had their issues, and then, you know, there was a period of time where basically tried to reduce the amount of liquid, minimum oil breakers, and started working with gases like compressed air. They worked actually quite well. We have had these technologies for a very extended period of time. Still, they have their limitations, especially for the very highest fault current levels. They may not have been good enough. And there comes the 70s where SF6 was introduced. So a arc quenching gaseous dielectric medium. And it looked like all the problems went away. This extremely performant gas that's good for arc quenching and for insulation purposes, as you definitely all know. But then it has its issues. Most importantly, its very high global warming potential, but also its decomposition products are quite toxic and corrosive. In the 80s, we had vacuum interrupters being introduced, extremely powerful technology. Currently, it's being tried to be extended into the transmission range. So new generations of vacuum interrupters actually for transmission level circuit breakers. The challenge there is obviously heat transfer, but other than this, it's a really neat technology. So when we're looking at this, we say, well, there's actually one thing that's missing here. And for this, we need to look at a phase diagram. And this is, so we need a medium that supports motion because we have moving contacts. So naturally, you look at gases and liquids besides vacuum, of course. But then there's actually one more option, and this is the supercritical region, which is a region that is accessible above a certain critical pressure and a critical temperature. So the fluids in that region, they have partial compressibility and very low viscosity, but they're extremely dense, which helps with thermal needs, but also with arc quenching needs. And it has actually a very high dielectric strength. So here are some of our own experiments on the left-hand side. You see the breakdown voltage, so to show the dielectric strength of carbon dioxide at the 0.1 millimeter gap uniform field. We measured values in the range of 25 kilovolt per 0.1 millimeter or 250 kilovolt per millimeter. So that clearly demonstrates the dielectric strength of the medium. Besides this, is at ultra low viscosity, excellent heat transfer capability. If it's CO2, it has a fairly low environmental impact, and obviously it's very cheap. This is why we're currently using this in a number of projects, most importantly, actually, our Edison hybrid DC circuit breaker. This is another project that we actually have with ARPA-E. We are about halfway into the project. It started 2 years ago, and we have another 1.5 years in front of us. And we've designed, built, and are currently in the testing phase of this disconnect switch, rated 12 kilovolt DC, 2000 amps. It uses carbon dioxide or mixtures of carbon dioxide with other materials. I'll come back to this later. And it uses a piezoelectric actuator to move the contacts extremely fast. It doesn't move them very far. We are talking about a 100 micrometer displacement. But it does so very fast, switching time around 250 microseconds. Now, this device does not have arc quenching capabilities or 10 amps. So this is actually part of a hybrid circuit breaker. This is not today's topic to talk about DC hybrid circuit breakers, but I wanted to introduce this to show we are actually working with supercritical fluids at this point. Now, when it comes to arc quenching, there's a whole lot more that matters. It's not just viscosity and dielectric strength. But what's just as important is really what happens with decomposition. So in an actual arc, when you ionize it and the gas decomposes, what do we end up with? Here in the center, I have a diagram what happened to SF6, where you get fluorine gas, you get solid sulfur, I mean solid when it cools down. And you get all sorts of other decomposition products. And this doesn't even include what would happen if there's any moisture in the system or any other contamination, maybe small amounts of nitrogen or oxygen, trace amounts of oxygen or so that are inside the circuit breaker. Now with carbon dioxide, it actually looks a whole lot better. So over the same temperature range, you see it stays mostly carbon dioxide. And as it decomposes, you get small mole fractions of carbon monoxide, oxygen also, obviously. And at the 10 to the power minus 10 ratio, carbon, solid carbon. Now the solid carbon obviously is an issue which needs to be addressed because it's conductive. So if that is found on dielectric surfaces, it could potentially be an issue. So I mentioned that we not only work with pure carbon dioxide, and here's where the trick really comes in. we can blend our supercritical fluid mixture towards their applications. And we have actually done so in our lab for quite a while now, tried out different mixtures. And each of these constituents, these substances that I've listed here in the first column, actually helps for certain functions that we want to achieve. Now, for the circuit breaker application, which has arc quenching needs, we are currently experimenting with small mole fractions of oxygen gas, which help to avoid carbon deposits, and it also helps to increase stability of the arc, or stability of the mixture after dissociation. So this, I expect, will give us a high life expectancy of the medium that we are using. Now, I'm sure many of you think, well, you know, at universities, they talk about crazy things, but obviously this is not realistic at all, because we've seen on one of the earlier diagrams, it requires really high pressure levels. This is just not realistic to build. And so I was actually under the same impression initially. I say, well, 8, 9, 10, 12 megapascal, that's a very high pressure level. Is this even manageable? Can we work with this? Can we build devices that operate at such pressure levels? And we've actually learned to do so. It is possible. The key element here that plays a very important role is that the high density of the medium allows us for excellent heat transfer, good arc cooling capabilities, but also for high dielectric strength, which in combination should allow us to actually shrink the volume of gas. And that is the key here, that we can actually reduce the diameter of the chamber itself of the breaker, so that we don't end up with extremely high wall thicknesses. So what you've seen in this is actually a photograph here, the disconnect switch. This is a wall thickness of about 3 centimeters, 30 millimeters, of a high-strength steel alloy. This is in part because it's a square, it's a boxy shape. As soon as you actually go towards a more round design, something that's based on a pipe, you can further reduce the wall thickness. Now, when it comes to the actual arc quenching mechanism, because there's a whole lot more needed to actually quench an arc. You have to control its temperature, you have to cool it, you need to allow it to extinguish at the natural zero crossing of the current. And there have been a number of technologies proposed to current SF6 switchgear technologies. Now, the way we look at this is we have to see what could be suitable for our supercritical fluid mixture. And the one key element to keep in mind here is our fluid is only partially compressible. As you can compress it up to a certain extent, but then you hit a hard limit where it basically turns into full liquid, fully dense, and then it becomes incompressible. So what we are designing is a puffer breaker mechanism that's non-compressible. So basically we allow the piston to actually move the medium at the arc through a nozzle, but without the need for the compressibility of the fluid, at least only up to a certain extent. So that requires a redesign, and we may give it a different name because it's not exactly puffer breaker principle. Now, we haven't started the project yet, but still we have the design partially completed. I cannot show all the details here. And we're already planning on the simulation and testing needs. We want to make this an actual realistic device that performs under all the switching conditions that it could actually see in application. So there could be normal switching conditions, there could be capacitive switching conditions, and inductive switching, depending on the application where the circuit breaker is actually used. And we are using a combination of synthetic test circuits at Mississippi State University, as well as testing at Kemah, Pennsylvania, where we can cover basically the whole range of conditions. And those that we cannot fully reach, there is actually a little bit of an issue of reaching 63 kiloamps symmetrical steady state RMS current. We'll try to cover those by computer simulations. So There's one more trick we have up the sleeve. You may have noticed that I've talked about a much smaller diameter pressure vessel for the arcing chamber. And that requires a few tricks to make it work. So here is a very much simplified computer rendering, basically showing how a three-phase arrangement could look like. And the trick that we have is actually we are using a actuator, hydraulic actuator that's integrated into the supercritical fluid inside the arc quenching, arc interruption chamber. So meaning we only need hydraulics line to basically go from the outside, from ambient into the chamber itself. And of course the bushings for the electrical power needs for the terminals. It also shows here an expansion vessel. We have to deal with pressure waves that are traveling through the device itself as it's quenching an arc. And we have to absorb basically the energy in that pressure wave with a compressible volume that's basically shown there, this expansion volume. The goal is to design, build, and test a three-phase 245 kV rated 4 kiloamp nominal current rated circuit breaker, which has a fault current rating of 63 kiloamps. Furthermore, we would like to keep the maintenance interval to 10 years and a useful life in the range of 50 years. The way we try to achieve this, I mentioned this at the very beginning, is by using mostly carbon dioxide, which is expected to give us a high life expectancy. So at this point, I would like to finish my presentation and give you a chance to ask questions.
Okay, I'm not seeing any questions in the chat right now, but we'll give folks maybe a minute. I had a question for you. Likely can't comment on specifics at this point, but perhaps you've thought about it because it sounds like you have another project that's closer to completion. Is there a commercialization plan for this technology once projects are completed and it's tested?
Yes, there definitely is. We are currently trying to address a niche market as a way to start building customer base and experience. And that niche market seems like it may actually be in the DC area, not AC. So that would be the Edison project. That's where we're currently talking to the Navy. So we're having shipboard applications in mind right now. But in the long term, we really see this as a potential replacement for substation applications. That's where we definitely need the help, the support from people here on the call, from NEMA, and we would be very interested in learning about opportunities to commercialize this technology.
Okay, thank you. A few other messages come in via chat. The first one is from Naeem Siddiqui. What about the life of contact system?
Right. So currently we have mostly experience with disconnect switches where the contact life has not been a major issue. Obviously that is completely different with circuit breaker applications that have to withstand arcing. We are working currently with a manufacturer, both two different manufacturers, one who helps us with the main contact system and the other one who helps us with the arcing contact system, and trying to solve a few challenges there. You're absolutely right. The CO2 environment comes with its own challenges, and we're trying to address those at the moment.
Okay, the next question comes from Fred Barbars. Is this applicable to distribution switches?
I definitely think it is applicable. The question is there a market for it? And we are trying to address this actually by customer discovery interviews to figure out where the applications could be. I see vacuum interrupters to be an extremely compelling solution for the distribution side. And one of the challenges that I see with vacuum interrupter technology is just to scale it to the absolute highest voltage level and current levels. But definitely, yes, I don't see a reason why this would not work at distribution voltage levels.
Okay, along those lines, Cameron Aladros asks, are you also modeling testing this application in lower voltage classes, 25 kV, 38 kV, etc.?
So excellent question. Again, we are currently not addressing this right now. So we basically have a medium voltage application for DC and this high voltage application for AC. But we would definitely be more than excited to talk more about this and explore this in more detail. Absolutely, yes.
Okay. Billy Lau asks, can you please further explain the oil actuator? Is it separate from the gas, or what is the potential of mixing with the gas?
All right, the actuator technology, yes. So that is an actual challenge. What we try to avoid, or what we do avoid, is having moving parts reaching into the high pressure volume. This is very, very difficult to achieve. So therefore, we said we only want stationary bushings and feed-throughs of any sort. And this is why we have decided to use hydraulic lines that reach from ambient into the switching chamber and have an actuator. We're currently working with Parker technology, Parker Hydraulics, to develop a hydraulic actuator that actually works under these conditions. And again, that sounds not very difficult, but it actually is, in part for certain carbon dioxide is a very, very good solvent. So the lubrication issue is actually currently the one we are addressing. But yes, absolutely.
Okay, the next question from also Naeem Siddiqui. How will you handle the complexity of CO2 mixture?
Yes, so the complexity is, so we work a lot with these fluid mixtures. We actually mix them even in-house, and in-house mixing is very difficult. So therefore, we actually have just started ordering gas mixtures pre-made, where we basically ask Airgas or so to prepare a mixture of 95% CO2 and 5% oxygen or something like this. Now, I do expect there are actually challenges to come in from a logistical point of view. Now, the gases should be easily accessible. Carbon dioxide and oxygen are really not difficult to find, but getting them at the right mixture ratio and everything, it does come with its own challenges. I clearly understand.
James Park asks, what is the lead time of CO2 disconnect switch at 230 kV from the point of receiving PO?
Our circuit breaker? Well, we first have to build the first prototype. So the timeline is, it's a 3-year project. And by the end of the project, we should have a first prototype built and tested both at KEMA as well as at a high voltage lab in Mississippi. Anything going forward from there requires probably additional investment. It may require further grants. It requires contracts. I think that there is several additional years before we can deliver prototypes or an initial series of devices to potential substation operators. So there's a few more years in between there.
Dragan Tabakovic is asking, is this similar technology to the seabed switchgear at 30 bars?
I don't believe it's similar in the sense of the nature of the fluid. A supercritical fluid has only partial compressibility. So you can compress the volume a little bit, and then you actually hit the full dense limit. And then it becomes almost like a liquid. And that completely changes all your design consideration with the whole switching mechanism, the nozzles, everything related basically that deals with these pressure waves have to be designed accordingly. That's the one big difference. So it's neither a gas nor is it a liquid. It really requires its own design.
Okay, and time for this last question from Jan Stauffer. What material are you planning to use for the breaker tank enclosure? Aluminum, stainless steel, etc.?
We are currently using in our DC circuit breaker or DC disconnect switch, we're using a stainless steel alloy. But we are actually, even there, we're actually switching to a aluminum alloy. We are currently mostly focusing on 7000 series aluminum. And if that goes well, we will probably do something somewhat similar to the Tesla circuit breaker.
Okay. And one final question again from Naeem Siddiqui. Is this new technology with CO2, do we still need to report the CO2 emission to EPA or any other organization? Is the emission of CO2 also subjected to penalty? I don't know if that's a question for you. That may be a question for regulators.
That may be a question for regulators, but I can add one more thing here, and this is we are actually trying to achieve a zero emission design, meaning we would not need any, so we would not use any soft sealing materials. So I've actually done this before for a completely different project. It was a cryogenic cable project where we had basically flanges that allowed welding around. So it's basically, it's all screw flanges and everything, but then you do a fusion weld around it, which basically eliminates any leaks at this point. So you have all metal flanges, all metal sealing gaskets, and then you weld it shut. And then you can grind it off. So you can design it for, let's say, 5 times opening or something like this. And I think our design would lend itself for such a technology. And that would then basically mean zero emissions, and it's welded shut.
Okay. A question, sort of the flip side of that coin, what is the expected GWP value?
Well, just below 1, I guess. Pure CO2 has 1. And if you add a tiny amount of oxygen, then it's 0.95 or so.
Okay. Dr. Graber, thank you again. I will ask you to put your, if you're okay with it, to put your email address in the chat so that folks can follow up with you with questions.
I will be happy to do so. I'd like to thank everybody for the excellent questions, and I'll be more than happy to answer more of your questions by email or even schedule a phone call and discuss this in more detail.
Okay. Well, with that, we will move on to our next presenter, who is Lionel Chilou. Mr. Chilou is the product director for GE's dead tank circuit breaker products. As part of this role, he oversees GE's SF6-free strategy in North America. He has over 22 years of experience in the power generation and transmission industry, including positions in product management, sales, and account management. Lionel, I'll turn the time over to you if you want to turn your camera on and share your screen.
All right, very good. Can you hear me, see me, Jonathan?
Yep.
Excellent. Thank you, Jonathan, for the opportunity. So we'll go through here a quick presentation on from a GE standpoint. What is our solution for SF6-free at the high voltage level? But we'll particularly focus on the ARPA-E award, that we got for 245 kV and up. So as a quick generic intro here, the SF6 regulation, there's so many drivers, right, in our market overall, but the SF6 regulation is the number one. And you can see quickly, as Professor Graber was showing, previously, since the 70s, SF6 has been a perfect solution for interrupting current, isolating and interrupting current at the high voltage side. It's such a stable gas, right? But as we know, it's really the worst gas from a GHG standpoint. And so then starting from the Kyoto Protocol up to now, in the US with California moving first, with the California Resource Board and a regulation into force. So there's been really an acceleration in Europe and in the US of regulation. And there's and so overall, it's a very strong driver, very strong signal for all players in the industry, utilities to start, in industrial customers, but obviously OEMs like us and the other ones. So I'll come back to what timeline, how did we get where we are now from a technology standpoint? But again, regulation is there, and if you zoom a bit So since early 22, so early this year, the revision of the CARB regulation is effective, right? And if you look at the dates here, I'm sorry, it's maybe small for many of you, but one key threshold, and I believe this is what ARPA-E was having particularly in mind for this funding announcement opportunity. So here, 245 kV, less than 63 kiloamps, so basically 40 kiloamps, 50 kiloamps, starting January 1st, 27, it means tomorrow in our industry, utilities in California would not be able anymore to buy new gas insulated equipment, so meaning outdoor equipment like a dead-time breaker or indoor, a GIS. A GIS can be outdoor, but so cannot buy anymore, 245 kV, 40 kiloamps, 50 kiloamps, and then, moving to 63 kiloamps. So it's really happening in California. It's a big market for sure, and then we imagine at least some states and EPA, at some point will come. So now if you pivot that to Europe, there's as well, and since longer actually, a very aggressive regulatory agenda, and soon, there will be that F-gas regulation coming. So all in all, the way to look at it, in our mind, it's not a question of if, there will be an SF6 ban, but when, right? So, and as we know in our industry, it takes time. It takes a lot of funding and a lot of disruption, a lot of innovation to change and to adopt change. So again, from a regulatory standpoint, all the signals are there and they are accelerating, right? So what did we do, GE? We started to work and we identify, many type of solutions, including vacuum bottles at some point, mixture, with only CO2, with very high pressure. And ultimately, we work with 3M, I believe, starting in 2008, to find basically what special molecule we could use, combining it, with CO2 and O2, making it a gas mixture. And we've been dealing, with gas mixture since very long. SF6 with N2, SF6 with CF4, for example, in Canada. And so that's ultimately, the solution we found to basically replace SF6, right? So it's first and foremost CO2, to oversimplify, 80% CO2, 5%, 15% O2, and the rest, that Novec 4710 fluorinitrile. So all in all, with that, because there is less weight, we do achieve, a 99% overall equivalent GWP reduction, same size of equipment, same temperature range. That's critical, right, for North America. Europe, lives and breathes by minus 25 degrees C. In the US, for sure, we go minus 30 or even lower, minus 50. So same temperature range, no voltage current limitation. That's critical in terms of scalability, right? Every utility we talk to tell us they want a solution that is universal. And also, they want the same level of toxicity or even better, but at least, the same level of toxicity than SF6, right? To which they used to from a training and process standpoint. So overall, we went with that solution. And as of now, we do have in service these three types of solution you can see here. So one, gas insulated line. So only using, that gas mixture that we call G cube, G at the power of 3. So we're using G cube, for gas insulated line. So we can take an existing insulated phase bus duct, and that's actually the one you see in a critical substation 420 kV in UK. Where we replace, some of the existing SF6 field gas lines and replace it by G cube ones, right? So a dramatic overall CO2 equivalent reduction. So it's kind of easier, right? Because we're not talking here about interruption, but just insulation. But then we went on the full solution, including the circuit breaker capability function, interrupting any type of current. And that's a GIS, complete GIS bay, gas insulated switchgear bay. And what you see here is one substation in, I believe this one in Switzerland, sorry, in Germany, but that's the first one we energized in 2018. And then outdoor equipment, including breaking capability with here a lifetime breaker. So we started with these three solutions, and many utilities, 30 utilities have adopted, and tried our solution. so far. So again, since 2018, we have some site energized with basically a breaker, interrupting current with that mixture. And you can see in bottom left some key names of some key utilities in Europe, and for example, on the national grid, our RTE, Réseau de Transport d'Électricité in France, Axpo in Switzerland, Scottish Power, and so on. So big name, big utilities, all having different type of technical requirements, and this is one aspect of it. One, it's about being compliant with standards. In that case, mainly IEC standard, even with some UK ones. But two, being able, to match their technical requirements, right? So you can see the number of bays we have in service and lines. So this is truly a strong experience. But that map is clearly not showing, anything in North America yet. Nothing 60 hertz, except, South Korea, and we'll come back to that. But as the market is moving, in North America, and because regulation is moving, and I want to say appetite or motivation of some big utilities is as well, moving fast. We were thinking, okay, how do we accelerate, development of a 60 hertz range? So we went to that journey, again, starting in 2008 with 3M to develop, that freon-nitrile molecule. Then we launched. Then we signed a license agreement with LS Power. That's LS Electric. It's a South Korean manufacturer. They wanted basically our support to help accelerate the development of some 60 hertz GIS bay for South Korea, as the main utility, KEPCO, is having a very strong agenda. But then we're lucky, to have two big funding coming from the EU, the European Union. One is for 420 kV, 63 kV GIS bay. So this one is very very ambitious. We're talking a lot of power, a lot of energy. And clearly a big challenge, right, to interrupt this type of energy without SF6. So 2019 we get that funding. Another funding, in 2021, this time for the outdoor circuit breaker. Then, as the market is pushing, for some hopefully few solutions, right, kind of merging and concentration of solution to make it easier, for utilities to share tools and manage their fleet. So at some point, we also signed a license agreement with Hitachi Energy, it's XABB. And so basically, since that point, they're using as well, that same mixture as we're using. Again, Novec 4710, sorry, CO2 first, O2, and some Novec 4710. And last but not least, again, to come to the point here of ARPA-E, awarding us that funding opportunity for 245 kV dead time breaker. So before I dive into it, just a snapshot here of LS Electric with their GIS bay 170 kV, 50 kiloamps, 60 hertz. So this is working really well, fully type tested in a record time using, again, that what we call G-cube gas mixture. Okay, I talked already about, Hitachi Energy, using that same mixture, and we can see some other players, also approaching us, to help them go faster, with that solution because of, first and foremost, its scalability, right? But okay, another regulation is one driver, funding is another one, right? You take the diversity of the ranges of equipment we have to convert, basically design to SF6-free, it's massive, right? And so here, funding opportunities, are a great way for companies like us to focus, specifically on one critical need. And in that case, for the ARPA-E one with the DOE, this is 245 kV, right? 245 kV and up, and first and foremost driven by California, but also many other utilities, in the US who want to move, even ahead of some regulation they would have in some states, and even of some regulation, the EP at some point would develop. So basically, this is the award we got. It's to start a 245 kV, 63 kiloamps, dead tank outdoor breakers, SF6-free, using our G-cube technology, and the way we look at it here, and what you see here is basically a snapshot of how we answered to the opportunity. We do have, we are developing a couple of first designs, for lower performances with G-Cube or for dead time breakers. But then based on that, and based also on the specificities of, which is more difficult than I see, specificities of the IEEE standards, the fact that it's 60 Hertz, the fact that we have to go minus 30 degrees, the fact that, there are some very specific performances in IEEE standard versus, the IEC one, that make it more difficult, to develop and successfully type test. So based on all that, we're designing now and starting to design around, thanks to that funding opportunity, 245 kV interrupter. If we're lucky, and that interrupter is quickly successful, then we can basically use it twice to make it a 500 kV dead time breaker. Today, that's you take our existing SF6 dead time breaker. It is twice, 245 kV interrupter. And so in best case scenario, out of this great funding opportunity in 3 years' time, we will have a very solid 245 kV base, to have an industrial version of a 245 kV dead time breaker, 63K SF6-free, and, potentially as well a 550, right? So there's some less, I want to say, rosy scenarios there, but okay, this is ultimately our goal. Just one point again, on compromises on performances, right? That utilities are ready or not to make, versus today what they used to for so long with SF6. The capability for a breaker to hold, line to ground voltage under loss of internal pressure. So you lose completely pressure of your tank, of whatever medium you have in your tank, gas insulated medium you have in your tank. Are you still able, to hold line to ground voltage right under that? So when you think about it, it's one of many key performances that has an impact on the size of the dimensions, of the size of concrete. But okay, that's some of the key performances, ARPA-E understood and that are challenging, and that's why they saw our technology and they're supporting us, to accelerate our development on the 245 kV design here. So, and what you see here, it's public information. It's basically our roadmap, moving forward on existing equipment. But again, thanks to European funding, and now DOE ARPA-E funding, we're accelerating, and focusing even more, on these needs. And also I want to add, these funding opportunities are actually great opportunities to partner with universities, right? So for our funding opportunity, we're partnering with Penn State on some specific, part of the performances at lower temperature. And Professor Cao will talk next, on some other key aspects of how do we develop, even solutions that would be easier for utilities to use, right? But funding opportunities helps in many ways, including, partnering with local universities, right? This is very important. Maybe just to complete a bit here the picture, we like to think trying to think, as a utility, what kind of criteria do you have to take into account when you go for selecting or trying an SF6-free solution? So it's a question of ratings. Again, what type of performances, are you ready to accept or even to compromise on, right? For example, do you have a breaker, what we call a universal solution? Today, with an SF6 breaker, you can interrupt anything and put it for any type of application, on capacitor switching, on reactor switching. But tomorrow, with one technology, you may not be able to have that universality of your breaker that you can put basically anywhere in your grid. Question of experience reliability, how disruptive is the SF6-free technology? How much risk basically are you ready to take also? How much experience in the field do you have or not? And it's not because the technology has experience, in medium voltage that you can directly say, okay, I can expect the same, on the high voltage side, because your requirements for availability at the high voltage side is by default way higher, right? An outage at the high voltage side does not mean the same, as a 25 kV feeder, for example. The change, what does that mean for maintenance and operators, people, at the utilities, in terms of how much of a change is it in the way to handle a new technology in terms of training, in terms of safety, in terms even some technologies, the higher kV, they emit X-rays. So what type of procedures do you have for X-ray? All that links to EHS for sure. Then the footprint, the weight of it, right? There is the solution itself, but then there is the impact of the solution on the substation design, on the concrete base, on for sure the cost. All that leads to cost. Cost, when I want to say 50% of all the factories building SF6 breakers will have at some point switched to an SF6-free, then the cost will go down. But how much down and how closer to an SF6 cost can an SF6-free technology be? And last but not least, we're doing all that, right, for sure, to reduce the environmental impact, right? So I'll come back to that if we have a bit of time, there's different ways to measure the environmental impact. One of them is GWP, but we'll talk more. Actually, now, let's take a bit of time now on that. So GWP, like we're saying, a mixture of CO2 is 1. A mixture of CO2 and O2 is less than 1. A solution with vacuum is 0 from that standpoint. But then when you zoom out and you look at the overall, what we call CO2 footprint of a solution, then, the picture can be different, right? We know CARB so far, is looking at it from a pure GWP standpoint. And our solution, for example, with G-Cube, depending on the products, but let's just say an outdoor dead tank breaker has a GWP of 300. So one could say, yeah, it's 300 times more than 1, but it's for sure less than 23,500, right, of SF6-1-2. But more importantly, in our mind, when you look at the complete life cycle cost, the life cycle assessment of a solution, in that comparison, and it's a C-grade paper, a solution using our gas mixture has less CO2 impact, 51% versus SF6, and vacuum because of the size, of the tank, the size overall of the equipment, the weight, how much aluminum, it takes, and it takes to mine this aluminum, to process it, and so on. So when you consider the entire materials, the losses, the manufacturing, the operational gas leak, the maintenance gas leak, the cost, and the CO2 footprint to handle gas leakage, and then the transportation and distribution of the equipment. When you check all that, the picture is not the same, right? So many utilities prefer that angle, of life cycle assessment. They see it as the more holistic and true picture, the true CO2 impact. Some regulation also, are looking at it this way. So just a way here for me to share, yes, GWP is one hand, but life cycle assessment, is the bigger picture, including the entire CO2 footprint of the solution. So all in all, it's just a quick summary of the different, what we believe, are advantages, of our gas mixture solution. But again, the R&D roadmap is changing and will keep changing. Because some big, utilities are coming and saying, okay, I want you to come sooner to the market, even ahead of the regulation, because I want a couple of years before the regulation comes effective. Or, like we're lucky and very, very proud of having awarded by ARPA-E, the funding helps us, to even accelerate and slow down on some program and focus even more on this, right? And I personally believe this one for 245 kV is perfect, again, in the light of California, and in the light also of many utilities, in the US who wants us to accelerate, right? So again, we want to thank ARPA-E for this award and for that trust. We look forward, to share progress all along the way as we accelerate our development of these. And you will see even that before that 245 kV, for sure, some products sooner than that, for indoor and outdoor application. So Jonathan, maybe we could switch to Q&A, or I have a few slides if you want, as you prefer.
Thanks, Lionel. Let's give folks some time to write some questions in. I'll again, I guess, kick off the Q&A with a question of my own. Gas handling complexities. Procedures, best practices, very, very established for SF6. Not so much for not just GQ, but any potential gas-based alternatives out there. Are there any additional complexities, mixing, anything like that regarding G cubed?
Yeah, no, that's critical. The way to look at it, it's not more difficult. It's the same as SF6, so it's not easier, but it's the same as SF6. The reason is we are delivering, pre-mixed already bottles, or for big GIS, substation, we are delivering filling carts that mix basically, the free molecules. So again, today SF6-CF4, breakers, for example, for Quebec. Same story, right? We deliver with pre-mixed, and the day you have a leakage, because this is law of physics, everything at some point leaks, small or big. And we all strive to make it as small as possible, but because CO2 is a very small molecule, one could say, okay, there is a differentiated leakage, but again, the way we design and type tested takes into account, for the entire life of the breaker, that you have a differentiated leakage. And we also worked on the gasket. And so you just need to refill and to top it off with the existing, pre-mixed bottles that you have, right? So you don't have at some point to rethink, of the gas mixture. It's all designed to take into account that and just refill, with your pre-mixed bottle. So I know Billy Lau is on with Dilo. We're working a lot with them, also with Air Liquide. They have a company they acquired called Airgas in North America, very active in North America, who are working with 3M, to be ready to deliver everything pre-mixed already. So the utilities won't have to deal with that.
It's worth noting that all three of those companies are also members of the SF6 and Alternatives Coalition.
Perfect. I did not know about the Air Liquide actually, but that's great.
Two-parter from Linus Farias. One, what do you project the change in the size and cost for 245 kV breakers that you are developing for dead tank breakers? And what is the change in size and cost for 145 kV available today?
Right. Thank you, Linus. On the 145 kV, same size. We may have just the interrupter a bit longer, the diameter is slightly different, but if you look at it from a weight standpoint and a footprint standpoint, you won't even be able to notice it. That's one. On the 245 kV, it's a bit early to say, because ARPA-E project is officially starting next week. It works by quarter, but same principle is the same. We just increase a bit the pressure, right? So basically we had 1 bar, so give or take will be a bit above 100 psi. But that makes the overall size of the gear extremely close to the one of a breaker of an SF6 breaker. So you can expect for 245 kV very small size difference. And again, we care about it for the cost standpoint, and I cannot yet answer on the cost, because cost will be a question of introductory point, right? And we have heavy R&D cost on all of this. But then there's the question of when the volume will start to really be there, right? Think about it. I think every year in the US, there are 8,000, give or take, SF6 new high voltage dead tank breakers that are shipped, right? So, and there's not that many factory, right? My point is, you need some volume effect to at some point talk about a stable cost. But we look at our design, we look at what is different from an SF6 breaker and a GQ breaker. There's not much difference, right? So at some point, we will have cost going really close to SF6.
The second part from Linus is, has GE considered replacing SF6 with an SF6-free technology for gas lines in gas-insulated substations?
Yeah, no, absolutely. That's what we do today. So we do have some cases. Okay, one building brand new substation in UK at 420 kV with gas insulated lines with G-Cube, / working on an existing gas insulated line or gas insulated bus, and studying it to see, okay, is the thickness enough to have a bit more overpressure, and is everything in good shape, so that we just have basically to remove SF6 and fill it fit it with G-Cube, right? So we're doing this type of surveys as well, and side by side, it's feasible or not, right? You may have to replace the entire GIL, or you could retrofit, just the gas for again gas insulated line. Now for gas insulated switch gear, meaning you have the breaker, the disconnect switch, the grounding switch, CT, VT. We have some designs that are coming where you could start, with SF6 and at some point convert to G-Cube. But again, you cannot do that, easily, right? Because the way the gas mixture behaves, the pressure for sure, but the way it behaves and interrupt and recompone and the byproducts, all that, is different. But we're working on having some what we call hybrid design, where you basically could accept both, right? So a customer could start with SF6 and at some point convert, right?
Okay, so we have about 6 or 7 more questions, but only 5 minutes, now 4 minutes. So we'll try and do these in rapid fire. Chris Barrett asks, are any considerations currently being given for maintenance intervals, costs, et cetera, when compared to SF6? If so, does GE have documentation to share with potential users?
Yes, same intervals, same maintenance procedure, same cost. So today you take your cost to maintain your SF6 gear. Again, an SF6 gear that leaks, less than 0.5, you will have same cost, for a G-Cube gear, outdoor or indoor. Yeah.
Stephen Barbera asks, how are leak locations identified? Can an infrared camera identify leaks?
That's a good question. I'm not sure. I'll have to follow up. I'll take a screenshot of that one. But today we have, sniffers that are for, G-Cube with gas mixture, ratio checking. And actually, Professor Kao next, we'll talk more about, okay, how do we take this, to the next level? But today you'll have the same factory acceptance test with the same requirements, of low SF6, of low gas leakage. And 2 on site, we have sniffers, and we're even developing more solutions, for that.
Noah Tai asks, is mixed gas suitable for retrofit applications of existing SF6 breakers with minor modifications?
The short answer, no, but it's not impossible. And so we'll see for what type of products, we could do it. For example, is your existing tank in the field designed to have, let's just say, 20% more pressure, right, of a new gas mixture? Can you easily change the gaskets? How can you retrofit, the interrupter on that? But short answer, no. But with the technology we have, it's not impossible. And at some point, we believe we'll attack that market.
Any plans for G-Cubed and high voltage instrument transformers?
Yes, we have some. It's not top, on the priority for North America, because again, I may be wrong, but we've not seen big installed base of SF6 insulated current transformers or VT. It's more a question for Europe, yeah. But so our focus for North America: outdoor breakers, dead tank, and gas insulated switchgear. Yeah.
Finally, Cindy Parsons asks, if CO2 leaks out, will adding more of the premixed gas mixture skew the concentration of gases within the mixture?
It will, but we've designed it for that. That ultimately the 2 functions of insulation and interrupting capabilities, and so it means electrical endurance and everything behind, both, would not deteriorate. Actually, it would improve as you do so. So we design it taking into account that, as indeed CO2 is the smallest molecule.
Okay. Well, it looks like no more questions, which keeps us right on time. Lionel, I'll ask you, just as I asked Lucas, to put your email in the chat in case folks want to follow up with questions. And we will move. One more. Are you working with other developers for one sound alternative to SF6?
Yeah, it's a very important question. Like you saw, right? So we have that license agreement with LS Power now, a license agreement with Hitachi Energy. Some other players, are approaching us. So this is part of what we do. We understand the industry overall will be successful in that transition if, there's a conversion towards one technology. And we believe, it sounds very arrogant, but we believe, this is the one, because most importantly, the scalability of it, right? You can see we're already demonstrating 420 kV, 63 kiloamps, so there's no limit to it. So there will be more announcement of more players using that same technology.
Okay, thank you, Lionel.
Thank you.
We will move on. Our third and final presenter is Dr. Yang Cao. Dr. Cao graduated in physics from Tongji University in Shanghai, China, and received his PhD from the University of Connecticut in 2002. He is currently a full professor at the Electrical and Computer Engineering Department of the University of Connecticut. Dr. Cao is also the director of the Electrical Insulation Research Center's Institute of Material Science, as well as the site director of the NSF Industrial University Cooperative Research Center on High Voltage and High Temperature Materials and Structures. Dr. Cao, the remainder of the time is yours. Dr. Cao, are you there?
Yes. So sorry that my computer somehow crashed. So
oh no. Oh, glad you could bring it back online.
Reboot it. So let me share my screen. Sorry about this. So can you hear me and see my slides okay?
Yeah, everything is good.
Okay, so thanks everyone. So this is Yang Cao from UConn, and I'm gonna take this opportunity. I want to thank Nima so that we can share with you the project that we just funded by ARPA-E regarding the detection and the fixation, a life cycle management framework for SF6-free power network. So this project will be in collaboration between UConn and General Electric. So at UConn, join me will be Dr. Steven Sub, who is a renowned surface chemist, and he's gonna bring in expertise relating to the fixation technology. And also on the project team, we have Dr. Krim Yonsi, who is an expert in the predictive maintenance and diagnostic and monitoring. And also we have Radislav Patorialo, and who is an expert in sensing. And also we have dotted line support from Yannick Kiefer, and also through indirectly from Dilo. So this summarizes the project team. So I wanted to thank the two previous speakers, Lucas and Leona, who has already set up the stage for my presentation, which actually make my talk a lot easier. So I will not go through the details that they already emphasized on. I think called in today that we have experts relating to SF6 and arc interruption in general. But I want to take this opportunity to highlight a few aspects that, and I want to thank that the ARPA-E for their visionary support. So first is not only SF6 has been proven technology, and there are very large scale of the installed bases of SF6 in use today, right? So, and now, with the emerging and or mounting concerns relating to the environmental impact of the SF6, keep in mind such large installed bases as relating to the leak detection and lifecycle management. We have a huge amount of need, and we have to keep those factors in mind when we outlook and seek for alternative solutions. And G3 is a very interesting gas mixture, and it holds the promise of replacing SF6 for arc interruption. So I just want to highlight here a few factors, and it has very high dielectric breakdown strength compared with SF6. We are talking about fluoronitrile, and when it is mixed with CO2, the liquefaction temperature can be tuned for cold environment. So just let us take a look at the molecular structure of this C4F7N, what make it unique, right? So, and we know SF6 is almost ideal arc interrupting media. However, it has a very long, and a high impact of the environmental, because of its inertness, right? So this C4F7N in comparison, right? So this fluorocarbon act like noble gas, while nitrile can be readily hydrolyzed. So by design, this molecule will have, less stable lifetime when compared with SF6. And that's part of the reason that it will have lower GWP factors. And this, as I already mentioned, this molecule, has a very high dielectric strength, and it can be 2 times higher than its main constituent. Cyanogen can be 2 times of the nitrogen, right? So, and also because of the CN group that balance this very strong electronegativity of the fluorine, that makes the liquefaction temperature would be not as high, right? So all this very uniquely combined together, making this G3 a very interesting and promising alternatives. We are not saying that it's ready, one-to-one, ready to replace SF6, and there are still, some additional work is needed, and we have a very ambitious plan, leveraging on this opportunity, with funding from ARPA-E, and to develop a life cycle management framework, which has 3 integrated components, so that to help us to transit from SF6 to SF6-free power network. And if we follow recent literature studies, there's a lot of contradicting reporting about the byproducts during arcing, and this, and I have to point out, many of those studies are not necessarily based on appropriate gas mixture like a G3. And in addition, they may not be conducted under well-controlled conditions. Oftentimes that we could see the testing environment could have contributed to some chemical species, detected during those study, and in a short, summary is that I would view those reported results at a stage, I think, unproven and requires additional study. And what we wanted to really to assure the transitioning to SF6-free power network is basically we want the first to conduct a physics-based decomposition model study. So to basically decouple those concerns that we have regarding existing studies. And in addition, we're gonna develop fixation solutions for unwanted aging byproducts, fixation, and furthermore, we wanted to develop a low-cost multi-gas sensing that will give us the capability not only for leak detection, and also for aging byproduct detection, right? So then we could have a very powerful life cycle management tool to fulfill those stretching goals of predictive maintenance and end of life fixation. And so basically our goal here is to basically, with the help from ARPA-E, we want to remove the barriers for the full adoption of SF6 alternatives. And we call the framework, meaning that we're gonna focus in this study, G3. However, we believe with additional development, the learnings we have, the technology we developed with minor adaptation and modification can be applied to other similar alternative gas for SF6, and can be further developed for the SF6 end-of-life fixation. As I just mentioned, we need to keep in mind there are huge installed bases of SF6-based technologies, right? So, if we are successfully transitioning away from SF6, we need a viable solution for SF6 end-of-life fixation. So here is just a few highlights about what do we plan to do regarding physics-based decomposition model, right? So it will be a combination of computational theoretical study with analytic experimental investigation based on steady state and a transient transition state study. We consider this being the key for the understanding of the physics-based decomposition modeling. Right? So, and then we can apply different computational tools and analytical tools. So basically we can derive the information related to the thermodynamic parameters of species and the decomposition pathways and the chemical reaction rates. Right? So, and we have developed over the years powerful tools based on local thermodynamic equilibrium, and then we can actually model the arc and arc interruption. And we want also, bring to attention is, as I mentioned, some of the existing study, they're not necessarily based on, a gas mixture like a G3. And a lot of early on study, they did not include, for example, oxygen, as Lucas and Leonel both point out that we could end up in the production of carbon during arc interruption, as highlighted here in this yellow curve in the computational study. So with that being said, we think that this physics-based decomposition modeling study give us the opportunity to truly assess the decomposition pathways for alternative gas, promising gas like a G3. Right? So we have developed, over the past few years, electrical aging testing for coronal discharge aging, spark discharge aging, with specially configured GC-MS for this G3 type of gas study. It can be extended to similar or other types of gas mixture, and we are in the process with the help from GE Grid Solution and the GNW Electric to study the high current arcing test. I bring all this up is some of the early on publication studies are actually based on questionable setup, and many are based on, for example, coronal discharging or spark discharge aging test, and in the environment that we cannot decouple the decompositions from, for example, the enclosure, right? So that led to a lot of questionable reporting of the byproducts. We wanted to do a controlled electroaging test so that we could develop a robust decomposition pathway. In addition, we wanted to be able to derive and extract aging signature, which is a specific to a certain duty cycle. And so we have some initial publications in this field. And I want to thank this community and particularly ARPA-E for their visionary support of this research. I have to say, over the even though SF6 used as interrupting media was studied in this country, and over the past maybe a couple of decades that we see going away of the research in this field. And this is really exciting that we see the coming back of the research in this very important area. And furthermore, if there is unwanted byproducts, with that understanding, and we have a very ambitious goal to design the fixation solutions, in a simple way, you can call it molecular sieves. So they highlighted here a few mesoporous in the UCT, UConn technology. It's UConn, I think, patented technology. It has a mesoporous structure, and with further tuning, it can be designed to basically trap and fix the unwanted byproducts. And remember, we also need a viable solution of fixation for SF6 end of service life. And the third component is a very powerful multi-gas sensing technology, from GE Research. And just here, we are at the very, we have not officially started the project. We received the award, and like any other teams, that we will be happy to report out the progress down the road. And what are highlighted here are, a few, features of this promising multi-gas sensing system, right? So it is powered with onboard data analytics, and it is quite portable and can be formed into sensor networks, and so it can be tuned for GIL, GIS, and different applications. And with what to be extracted, the aging duty cycle specific byproducts information from other tasks, and this can allow us, to extract information as related to the aging signature, in addition to leak detection, right? So, and this technology has been highlighted at the Nature Electronics, which is one of the top scientific journals, and also received other awards. So this is a really interesting and a promising technology. So with all these three components that been developed, we are at the promise to develop and deliver down the road a life cycle management, for this SF6 alternative technology. And this is the area my former colleague and a collaborator, Karim Yancy, and who prepared this slide. So I'm just highlight a few here. Is so this life cycle management system is enabled and powered by optimized distribution of advanced sensor network, right, to sense G3 components and the key byproducts. And obviously, this will be further identified with more, controlled and refined study. And it's natural to vision that we'll have data fusion, and we'll develop a new sensory data, and all that you can, including some virtual sensory for reliable insulation gas mixture operation state, right? So this is a very important capability, and we can estimate reliably the gas mixture homogeneity, density, and the composition during the service life, right? Then we will have will be able to develop algorithm for high fidelity prediction of gas mixture, and as relating to its arc interruption capability, and furthermore, can give the utility members the user recommendations as relating to the maintenance, predictive maintenance. So this is what has been published with announcement. So we have a very high, a very ambitious goal, and so what we want to focus on, starting from G3, develop this life cycle management framework. We want to focus on leak detection, agent byproduct detection, and fixation by capturing and storage the unwanted agent byproducts, and this, powered with the proposed sensing technology, will enable life cycle management. And we believe with the further development, this framework can be further extended for other promising technology, and more importantly, can be applied to retrofit existing asset for SF6 leak detection and end-of-life fixation. So, thank you for your, for this opportunity to share with you this project. So we have not officially started, but we'll be happy to update you during its research course. So thank you.
Thank you, Dr. Cao. I'll kick it off with a question. Do you see this lifecycle management being like a software-driven analysis that plugs into like a utility SCADA system, or is it a different type of framework?
So it including physics-based decomposition modeling, which will be experimental-driven study. And it also includes development of targeted, if you call it molecular sieves for fixation and sensor network. But to your point, the outcome could be an analytical tool that, based on all this capability enabled as outcome of this development, could be developed into like asset management tool for utility.
Okay, thank you. One question from Noah Tai. Could you comment on the recovery time of G³ versus SF6 from the plasma state to the dielectric state?
Novak Novak itself actually has a higher dielectric strength, right? So and as relating to the arc interruption, and the G has done extensive study and to ensure that the optimal composition of this gas mixture will have equivalent arc interruption capability as SF6. So I'm not sure that does it answer the question.
Do we have any other questions or a follow-up to that one? While we're waiting for other questions to come in, I'll ask you to maybe comment. You mentioned a few times the potential to adapt the framework or the output of your projects to any other alternative gas. In order to do that, would you sort of need the same resource and investment to adapt the model to every additional alternative gas, or once you've completed this project, do you have enough of a template down that it's much more flexible?
I think this methodology, obviously is a key, right? So and we are, also not saying that this will be readily, available for other, even though similar types of alternatives. So, but we believe that with some additional development, not like we need to do it over again. For example, the sensor networks, for instance, that probably with some fine tuning and the training of this sensor networks that can be adapted to, another type of alternative solutions. But I personally see that we have the same need for other types of alternative gases, and regarding the physics-based decomposition modeling, sensing, and fixation, and particularly physics-based decomposition modeling. And I just highlighted here C4F7N, which is the ingredient for G3, but I have seen other complicated decomposition passes for other types of alternatives, and I don't believe that they are, they are done in a thorough and bulletproof way. So.
Okay, thank you. Noah Tai sent in a follow-up question to his prior. He restates, does decomposition suggest there is wear and tear of the G-cubed gas?
That's obviously a very key question. But based on what first of all, given the volume of GRS and the interrupting media for each interruption is a small fraction. And also, I learned that there are pilot switch gears in operation for quite a few years, and I think it's definitely a good indicator that the so-called wearing probably is something that could be well under control. So I think the optimization of the gas mixture as related to specific arc interruption duty, obviously, also the environmental concern. We need a very high, very system level optimization. So so far, look pretty promising. So
okay. One last question from Linus Farias. What is the phase state of the fixation byproducts of spent SF6? Can you confirm that this is a physical fixation and not a chemical fixation?
We are actually quite early on, but that's a very good question, because we are doing some materials compatibility study, including the molecular sieves. So and also the shape selectivity of the molecular sieves definitely is an important knob. So my limited discussion with my collaborator, Dr. Sub, I learned that there are, even for one specific type of molecular sieves, there are many derivatives. So I think that we're probably going to use a combination of, shape selective, and with certain aid of composition for chemical. But it's too early, and I probably would rely on my collaborator, Dr. Sub, to help us more on that, or maybe with that question in general. So.
Okay. Well, thank you very much to Dr. Cao and to all of our presenters. As I mentioned at the outset, the slide decks as well as the recording will be posted online I posted 2 links early on in the chat for the SF6 and Alternatives Coalition LinkedIn page, as well as our website. And Dr. Cal, like the other presenters, I'll ask you to put your email address in the chat so that all of our guests, any that have follow-up questions, want to contact you, can do so by email. I want to thank all of our presenters today, as well as our audience for joining us. I hope it's been a productive use of the last 90 minutes, and I look forward to maybe a year from now, having kind of a post-mortem. Maybe that's the wrong word, but once projects are much further along, we can have a status update. Before closing, I also wanted to announce, by way of upcoming events, a training event that the SF6 and Alternatives Coalition will be convening this summer, precise date to be confirmed, in California. We'll be doing one in Northern California and one in Southern California on GIE nameplate adjustments. Those on the line from a California utility, likely others as well, are aware that the new CARB regulations allow for utilities to adjust the nameplate of the gas insulated equipment at installation if necessary, so that it more accurately reflects the gas density needed for proper insulation. The SF6 and Alternatives Coalition worked with CARB for several years leading up to this point to get this allowance in place. So now that we're across the finish line there, we want to provide training to the regulated entities on how to go through the nameplate adjustment process that's outlined in the regulation. Throughout the day, we'll also share information about SF6-free technology currently on the market, as well as some presentations on other aspects of emissions reporting and the new regulations. So please stay posted for more information on that event. Thanks again to everyone, and we look forward to being in touch.